Hello everyone, this is video 2.4. We're going to be looking at comparing fractions, inequalities with fractions. I don't know why the book just doesn't want to say inequalities, but so we're going to be comparing fractions. I'm going to take a little different approach to this video. I'm going to go through four methods, and so we'll look at sort of the reasoning behind each of these methods, but there's going to be a lot more sort of methods based, so there'll be a little bit more structure to this video than a lot of the other ones. So let's get started. Okay, so method one, we're going to convert to decimals. There's a lot to like about this method. There's a lot to not like about this method. So we'll go through the method first, and then we'll talk about sort of the pros and cons of this method. So let's look at an example. Let's say we're comparing 2/7 with 3/11. So we want to compare these. So we convert these into decimals, and so 2/7 is 0.285714, and then these six digits repeat. So it would be another 285,714, 285,714, so on, so on, so on, so on. And now 3/11, we convert this. This is 27, 27, and the 27 repeats. And so using what we talked about in the previous class in chapter 1, we start with the largest place value. So there's 2 and 2. So those are the same. And now we go to the next place value. The 8 is bigger than the 7. Aha. So this one is bigger, and we know that 2/7 is larger than 3/11. There you go. That looks terrible. I got to fix that. That's going to bother me, but not to the point that I'm going to restart this slide. 2/7. There we go. Okay, so what's good about this? That it's relatively quick. If we have a calculator, and so we'll put a little, it's quick with an asterisk. If for fractions like this, for 2/7, 3/11, if we have a calculator handy, or if we happen to know a lot of the rules around these decimals, I mean, there's a way to be able to do this in our head, and there's a way to be able to do this in our head. But for a lot of students, they're probably not going to know these decimalization patterns for numbers like sevens and 11s and things like that. And they're probably not going to memorize, the 12ths. Most students are not going to know 1/12 off the top of their head. So it's quick, assuming you have a calculator. Um, the process of comparison is fairly direct. So we have a direct comparison method. So once we get those decimals, comparing the decimals is fairly straightforward. Now, the big con for this is that it assumes decimal fluency. We're kind of robbing Peter to pay Paul here a little bit. If we're talking about fractions, I kind of prefer to be talking about fractions. Now, I don't have a problem with this method necessarily, but if students are always converting fractions into decimals, then effectively they're just learning about decimals and they're not really learning about fractions. And it's sort of my contention that this is what happens with a lot of students is every time they see fractions, they sort of freak out and they're allowed to just pivot everything to decimals. And so you do that for a couple of years, you just don't develop any competency with fractions. So I don't mind this as a method, but I would really prefer to put this way at the end and say, okay, well, once you've shown me that you can do these methods where we retain them as fractions, now we can start using them as decimals as well. So this becomes a support rather than the primary method. So that's method one, converting to decimals. Method two is common denominators. And so we could start with a relatively simple problem like 5/7 and 6/7. And so we can see that these two fractions, they have the same denominator of sevens. So which one is greater? Well, we want to look at having more parts. I mean, it's pretty direct. So if we were to draw number lines for this, so 1, 2, 3, 4, 5, 6, and then 7. So 6/7 we can see comes up to here, and 5/7 comes up to here. Is a special case, and you know that the denominators are the same. Although we'll see in a moment, we can make every case fit this if we really are inclined to. Um, so we can see that when we have the same size pieces, and this is a big theme in the previous slide, the 2, 3 slides, that when we have the same size pieces, things are a whole lot easier to compare. So once I have these both as sevens, you know, I know that they're the same size. So 6 or 5 of the same size pieces, I know 6 is bigger. Now, if we look at the previous problem where we had 2 sevens and 3 11s. Now, these are not the same size pieces, 1s and 7s and 1s, 11s. So it's hard to know, is the 3 really more than the 2? I mean, there's the 3s, there's more of them, but they're smaller. And we'll talk about how we know they're smaller here in a moment, but we know that we can tell that they're smaller once we get to that point. So what we're going to do is we're going to make these so that they are the same size. So as we saw in the previous slides, we know that these are going to be 77ths as our pieces. So we're going to multiply this by 7 over 7, so this makes 21. Multiply this by 11, and this makes 22. So once we have the same size pieces, now we can just compare the numerators, and it's a fairly direct process from here. And as it turns out, that the 3 was more pieces, but they're just that much smaller, so that 3 of these pieces is actually less than 2 of these pieces. 3 11ths is actually just a little bit smaller than 2 7s. So the pro for this is that it retains fractions. So we're doing a fraction problem that deals with fractions. Rather than converting it to decimals, we're building fluency around fractions. Now, the con for this is that it's probably a little bit more complicated of a process. You could certainly argue that it's a little bit, there's a little bit more of a mechanism that's going on here. We can't just grab a calculator and generate a decimal. So we could certainly argue that the con for this is that it's mechanically more complex. At least for some students. I mean, it's the worst we're doing is multiplying by 11 and multiplying by 7, but we have to know how to do that. It's still dependent on that. But if we've built that process up before, then you know it's an application of this thing that we just did. Planning a lesson plan. This might be day 3, where day 2 we did that equivalent fraction piece. And so once we've built that, we're going to apply it the next day to this process. But this is method 2, getting common denominators. Now, method 3 is where we have the same numerators, where we have a common numerator. So let's compare, say, 7 11ths and 7 13ths. And this is where we can do a little bit more reasoning now about what the denominator really tells us. I have 7 pieces here that are 11s, and then 7 pieces here that are 13s. Of the same number of pieces. And I really like this question because it really makes you think about what a denominator is and what it really tells us. So here 13 pieces make up a whole, and here 11 pieces make up a whole. So which one do you think is bigger? It's a little counterintuitive for some students, but this 13th, the larger the denominator, so our larger denominator is going to mean smaller pieces. And it seems like an almost like contradictory thing that larger makes smaller. But I mean, if you draw a model for this, if you draw a rectangular model for one and a rectangular model for the other, I mean, even if you don't want to do 13s and 11s, I mean, if you just compare fourths and thirds, I mean, you can see that the 1/4 because there's more pieces of the same whole. Now, again, we're going from 0 to 1 being the same thing. Um, there's more pieces. We have to break that whole into more pieces. It should make some degree of sense that the pieces then have to be smaller. Again, the language behind this, anytime, some students are going to see larger equals smaller, there's some dissonance there. That doesn't quite make sense. So a physical model of this to help this make sense is going to be helpful for a lot of students. Might be helpful for you as well. But this 13th is the larger denominator, so these are smaller pieces. So the 7/11ths is going to be larger. It's the same number of pieces, but the pieces are bigger. So I have the same number of bigger pieces. That makes this um, that makes this the larger fraction. Now, if we do the same thing with our 2/7 and 3/11, we're going to use the same idea. And it's interesting because we do problems where we find a common denominator a lot, but there's some value in using a common numerator as well. And so we could multiply this by 3 over 3 and multiply this by 2 over 2. And so we get 6 over 21, and then we get 6 over 22. Again, same number of pieces, but we know that these are just a little bit bigger. And so again, we've seen a third way that 2/7 is bigger than 3/11. So we've seen it by decimal, we've seen it by common denominator, and now we can also show it by using this common numerator method. 6 pieces that are a little bit bigger versus 6 pieces that are a little bit smaller. The pro and con for this are pretty much the same as they were for common numerator. The pro is that we're still building fractional fluency. So we're still building ideas around fractions. And the con here is that, yeah, it's more mechanical. Probably even more so. Well, no, mechanically it's the same as common denominators, but it's more mechanical. Plus, it's probably a little bit more. It's a little bit more conceptual, because now we have to think a little bit more about what that common numerator like genuinely means. So there's a little bit more thought into it, but that thought is going somewhere. It's going. I mean, this is the trade-off. It is more conceptual, but it's going to building ideas around fractions. So there is meaning and there is purpose behind it. So the fourth method is what's called the benchmark method. And it's not really always going to be applicable, but where it is applicable, it's really helpful. And I really like seeing how students can apply the benchmark method and think about the benchmark method. What we're going to use is we're going to use comparisons, sort of using the what's called the transitive property. We're going to use a third fraction in there where we know the two fractions that we're working with have a relationship with that third fraction. So to give you an example, let's say that we're going to compare 4/5 and 7/6. And so the first thing you might notice is, hey, this is a proper fraction and this is an improper fraction. And so what you're really noticing is that this one is greater than 1 and this one is less than 1. And so this is what I mean about this transitive property through a third fraction. We're using this 1, which we could think of as a fraction because it is representable as a fraction. We're using this 1, and this is my benchmark. I'm using comparisons to some third number, in this case, the 1. So if 7 is bigger than 1, and 1 is bigger than 4/5, then I know that 7/6 is going to be larger than 4/5. We can also use this with other fractions besides 1. So if we were to take, say, 4/5 and 1/3. And so the benchmark that we might use now, that's terrible. What happened there? So the benchmark that we might use here might be 1/2. So let me give myself some more room here. So I can compare this to 1/2. And I know that 4/5 is bigger than 1/2. And I know that 1/3, using my common numerator reasoning, is less than 1/2. So my 1/3 is less than 1/2. So now I'm using my 1/2 as my benchmark. Students probably aren't going to be able to use things like 1/3, 1/4, things like that as benchmarks. I mean, there's only going to be certain fractions that most students are going to be able to use. The 1 is a pretty obvious one. We've got proper and improper. I mean, they're even named when they're on different sides of that benchmark. And the 1/2 is pretty easy for a lot of students because all they need to be able to see is if the numerator is more or less than half of the denominator. So the 4 is bigger than 2.5. The 1 is less than 1.5. So that's a little bit easier to tell. Other fractions is going to be a little bit harder to tell what's going on. But getting students to be able to see this, when you recognize it, when this is the case, it goes quick. So a real pro to this is that when it's applicable, it's very fast. I mean, once you make those comparisons, once you recognize that it's there, then the problem gets solved relatively quickly. It builds a lot of understanding about what's going on. It makes you really think about a lot of the methods that you used in the past, but it's relatively quick. The big con for this is that it's a very narrow scope of cases. This isn't always going to work. And in fact, if we were to look at our 2/7 and 3/11, it's hard to make this method work. It's hard to find something in between these two to use as a benchmark for 2/7 and 3/11. It's possible. I mean, we certainly can. But as much work as we would put into finding the benchmark for this, we could probably put into using one of the other methods and actually get the answer a little bit more directly. So it doesn't always work, but when it does work, it works really well. Okay, this fifth method is kind of optional. I don't even think it's in the book, but I want to talk through it real quick. And it's called the residual method. And so it's again like the benchmark method. It's not going to be applicable to every single case, but where it does come up, it's really nice to use. And it's sort of an extension of the denominator method. So let's compare 3/4 and 5/6. What we might notice from this is that in both cases, we're missing one piece. So we are missing one piece. And this is the special case that we have to have. It has to be missing exactly one piece. If this were 3/4 and 5/7, this isn't going to work out as well because we've been missing one piece and two pieces. So what I notice is that I'm missing 1/4, and here I'm missing 1/6. Because this is the smaller piece, and again, this is why it's sort of an extension of the denominator method. I know it's a smaller piece because it has the larger denominator. So my larger denominator is going to tell me that this is the smaller number. So because this is the smaller number, I know the 5/6 is bigger because it's missing the smaller piece. It is closer to being whole. This is again much like the benchmark method. When you recognize it, it's very quick. Once you recognize it, the con to this is it's probably just as, if not more, narrow of scope. This is such a, I don't say rare, but it doesn't come up an awful lot. But it's a good thing to look for. And again, when students can recognize this and see this, it really shows you that they've developed a lot of fluency around fractions. So this is what's called the residual method. Again, doesn't come up an awful lot, but still good to know. Okay, method 0 is this thing called the cross multiplication method. And as you can see right there in big letters, I want you to avoid this. Now, as much as I say I want you to avoid this, I know in my heart some of you are going to do this anyway. And you're going to see other teachers do this, and you're going to see teachers sort of, talk about this method. But I want you to really avoid this method if at all possible, and I'll show you why. Let's go back to the previous problem that we just looked at, 3/4 and 5/6. Okay. And what you'll see teachers do is they'll say, okay, well, we're going to multiply 4 times 5 makes 20. And then I'm going to multiply 3 times 8 is 18. And so because the 20 is bigger, I know the 5/6 is bigger. All right. Now, realistically, sorry about that cough. Realistically, a lot of you probably have recognized already, really this is just common denominator. That when I'm multiplying by 4, what I'm really doing, and here we'll write this out, 5/6. So we're multiplying by 4. That's what this 4 is. It's getting us 20 over 24. And then this 3 times 6 is we're multiplying by 6, and so we get 24 here and 18. And so we're getting a common denominator of 24. And then I know I have 20 pieces over here. So 20 24ths is bigger than 18 24ths. Comparing this 20 with this 18 is the same thing as the common denominator method, right? Wrong. Because students who are doing this method up here without seeing this have no clue why this works. None. And I've seen more than a handful of students, it's a really common thing for students to do. They see this method, well, they multiply like this, and they get 20 and they get 18, and they say, oh, okay, well, 20 is bigger, so 3/4 is bigger. And so you're in a position now where students are going to ask, well, how come it works when you multiply up, but doesn't work when you multiply down? And as soon as you hear that question, you should sort of recognize that the students are doing math without having any understanding of what it is that they're doing. Multiplying up and multiplying down are relatively arbitrary ideas. Okay, so that's why I don't like this method. Now, if you want to do this first, do the common denominator method first, and then say as a shortcut, we can see this. You could do that because then at least this method is built on something. But even then, realistically, you're not saving yourself that much time. I mean, you're saving yourself writing a 4 and writing a 6. You're saving yourself having to write two numbers, but what you're sacrificing is an awful lot of concept, an awful lot of understanding. And I don't think that's a very good trade. I think you're a whole lot better off writing out the whole thing so students can see what's going on. It's not that much, and it helps you avoid cases like this where you're trying to offer explanations that really don't make that much sense. So this method, in your field work, you're going to see teachers who, when they're teaching this, you're going to see teachers who do this. And I'll tell you right now, just because you see a veteran teacher do something doesn't mean that it's worth replicating. It doesn't always mean that it's worth doing. A lot of teachers, myself included, have made and make mistakes. All right, so and I'm telling you right now, this is one of them. So really, really, really try to avoid this method done this way. All right. So for our checkpoint problem, here's four fractions: 5/11, 5/7, 2/5, and 7/9. And what I'd like for you to do is try to put these in order from least to greatest. And you can use whatever method or methods of your choice. If your instinct is to just change them all to decimals and order them that way, that's cool. But I also want you to think about doing it in a way that's not strictly decimalization, right? So if you want to use decimals, that's fine, but don't just use decimals to do these problems. Again, we want to think about fractions as fractions, not as a special case or a special extension of decimals. All right. If you have any questions about this problem or anything from the slide, talk about it in class. Thank you.